Hello world, this is Morris, and I've been working on this Neurocave web app. So here it is, visualizing a regular connectomics data set, and I've added some more of these glyph size control sliders so that you can decouple the spheres and cubes on the left and right and control their sizes individually. This will come in pretty handy for the data sets for the Allen Brain Institute that I've imported. And I also have these these edge weight sliders over here, so you can independently control the contralateral and ipsilateral edge weights, and you can also have check boxes that make the ipsilateral and contralateral edges disappear in this mode here, and you can unlock the left and right colorings, so you can have, like, say, a modularity Q coloring on the left with an isomap dimensionality reduction embedding the brain. You can compare brain connectomes with the native colorings for their different dimensionality reduction embeddings, and there are also have animations for the selected and connected nodes, and you can control the amplitude and frequency of those. So when you visualize when I import this Allen neurogenomics data set, it's I downloaded it here. It contains both MRI and microarray data for these 8 donors. 4 of them have diffusion tensor imaging, so I extracted their connectomes using the DTI T1 T2 weighted MRIs, and they also have microarray data, so they have 62,000 probes per profile, per donor, per brain, and they have 500 samples per hemisphere, so that's about 1,000 samples per brain. And so they map the 3D coordinates of the samples with the MRIs. So I imported all of that data, so I now have the 3D coordinates of all the samples, which I'm displaying here, and I'm in the foreground of this scene, and in the background I have a UMAP dimensionality reduction embedding of the genes with their co-expression values from a WGCNA hierarchical clustering weighted gene co-expression network analysis. So I'm gonna in this view I'm gonna switch to have the gene UMAP analysis in the foreground, and in the background, way back there, that's the brain, and so I have the brain. The brain regions are displayed as spheres, and the gene glyph markers are cubes there. So I can decouple, unlink the boxes and spheres in the left and right sides, and so I can adjust the sizes to optimally display And so now we can do a search. I have a search box that I've enabled, so I can search for a gene that I'm interested in, like SLC. That's the from this. This is let's see. I'm looking for some monoamine transporter genes. So it looks like their gene symbols SLC, and you can see that they have a web interface to their data with a heat map there. So I'm going to have that data visualized as a node link diagram graph over here. So this is lighting up and selecting the SLC genes, and it's displaying the edges, show what genes co-express with them, and also the edges that go over to these brain glyphs in the background. They this scene here shows how they connect to brain regions that express these genes. So I'm going to keep clicking this. I'm going to find all the SLC genes. So that stands for the solute carrier family, vesicle monoamines. These are all the genes that I'm interested in, and I'm seeing the brain regions that they're connected, that they're expressed in, and the genes that co-express with them. I'm just going to keep clicking these and get as many of these as I can. Okay, that's probably enough. Now, at this point, I can adjust the weights. So I have the intergroup weight, which is the weights linking the genes to the areas they're expressed in. So I can show more or less of those by adjusting these weights. The intragroup weights, I can set them to show the edges that connect the genes that co-express with one another. And I can change the threshold mode so that it just displays the 5 or 10 most the top connected genes and the brain regions. So if I'm not interested in intergroup edges, then I can click those away with that checkbox. Now I'm only seeing the intergroup edges. I haven't selected any brain regions yet, so I can set the opacity of the edges down so that they're kind of transparent, and I can turn on these animations so that I can have the frequency and amplitude of these pulsating things, so I can make those glyphs stand out. And now I can see which brain areas are affected without having all of the edges cluttering up the scene. I can select them So maybe if I'm interested in the ones in the forebrain, got the superior frontal gyrus there, and the medial orbital gyrus. So I can see the edges that are connecting them in the, and on the, I can see the edges that represent the connectome connectivity of these high monoamine transporter expressing genes. You can also see genes that co-express with the monoamine transporters. So there's a lot of exploration and browsing analysis that can be done. We also have, we can uncouple we can unlink unlock the left and right color scheme, so we can keep the left anatomical coloring, and we can color the genes, the gene UMAP embedding based on something else, or maybe we can keep that one. Or yeah, maybe that one can be this combined signed and unsigned WGCNA clustering colors. And on the left, maybe we can do a degree connectivity range, so we can maybe gray out the low connectivity, the low degree connectivity brain areas, and filter out the ones that are highly connected. Find the most highly connected areas of the brain. Well, let's do the second highest. Alright, so it looks like the superior frontal gyrus and the middle frontal gyrus are in the medium-high connectivity range, and they have a high degree of expression of these monoamine transporters. Yeah, that's what we learned today in this Allen Brain Institute neurogenomic data set analysis using Neurocave. Thanks for your attention.